We're going to talk about section 1.6 in our book, Powers, Polynomials, and Rational Functions. In particular, their behavior, the behavior of their graphs, and what we call order of magnitude. So a power function is anything that takes on the form y equals kx to the p, where k and p are constants, so x and y are the variables. So some examples, you can see in the yellow, these all have positive integer exponents. So y equals x to the second, negative 2x to the third, positive 3x to the fourth. We'll talk about those to start with. A little bit later, we'll talk about these kinds that you see in the green that have negative exponents, or as if we can write them with x's in the denominator. And then a little bit after that, we'll talk about fractional exponents. So the graphs and behavior of a square root and a cube root that's in the denominator and so on. Okay, so talking a little bit first about these power functions in the yellow. So we're going to focus on this first. So in particular, if we look at what happens to evens versus odds, so the whole even versus odd issue. So the noteworthy behaviors are, x to the second, we hopefully recognize is going to be a parabola, and negative 2x to the third is going to look something like this roughly. So the negative is going to reflect it in the x, and the 2 is going to stretch it. 3x to the fourth will look sort of parabolic, but it will be even steeper, and then the 3 is going to stretch it and make it steeper still. But the even versus odd issue, we can see that anything that has an even power, it's going to come and go in the same direction, and odd functions will come and go in different directions, in the opposite directions. Okay? We also want to note that higher degree power functions dominate. So what I mean by that, if I do a rough sketch here of y equals x squared, x to the third, and x to the fourth on the same axes, all of these will contain the point 0, 0, and also contain the point 1, 1. Now x squared being even will come and go in the same direction. And in particular, we're going to notice the quadrant 1 behavior. Now x to the third is also going to contain 0, 0 and 1, 1. It will also contain negative 1, 1. But what will happen is it's going to, if I can do this right, it's going to get even steeper faster there. So after they pass through the point 1, 1, the green function x cubed is going to get bigger faster than the yellow function x to the second. And similarly, x to the fourth is going to, and you're going to have to use your imagination here a little bit, it's going to be even steeper still. So I'm not doing it very good justice there, but it'll look sort of like a parabola, but be even steeper. The point being that if you look at this behavior in quadrant 1, that once they passed 1, 1, as x gets bigger and bigger, as x approaches infinity, we're going to see that x to the third will get bigger faster than x to the second. So a higher degree is going to get bigger faster. That's known as, so in general we can say x to the n is a higher order magnitude function than x to the m anytime n is bigger than m. So the bigger the exponent, the higher order magnitude function. And what we mean by that is it's got this property that it's going to get bigger faster. Okay? All right, let's bring up the here. And let's talk about polynomials. So a polynomial is, you can sort of think of it like a bunch of power functions being added or subtracted, except that a power function could have a negative exponent or a fractional exponent, but for a polynomial, these powers are all going to be non-negative integers. So like we saw in the earlier screen, the higher degree is going to get much bigger and faster than any smaller degree. And so the behavior of a polynomial, the end behavior, will be determined by its highest power of x and its coefficient. So the end behavior is determined by the highest power of x and its coefficient. That's sometimes called the leading coefficient test, if you remember. Okay, so let's look, for example, at some cubics. So we have here in the yellow y equals x to the third. So if you remember from your AP prep days, it's going to have an x-intercept at 0, and this is sometimes called a 0 of multiplicity 3. It's going to swirl as it crosses the x-axis. So there's an example of a cubic. And this is another cubic because its highest power of x is x to the third, but it's going to have a 0 at 0 and also at 1. It's going to bounce, if you remember, from your cross bounce swirl and then cross. So there's another example of a cubic. And if we multiply this out, it would also be a third degree. And it has zeros at -1, 0, and 1. And these are all to the first, so it's going to cross, cross, cross. So these are all third degree polynomials, but you can see they have slightly different behavior there. Okay, notice that you have at most, since it's a third degree, you have at most 3 minus 1, 2 turns. So the x to the third didn't actually turn at all, so it had 0 turns. It did not change direction at all. The green one, that's another cubic. It turned once at the 0 and again somewhere over here. So it had 2 turns. It changed direction twice is what we mean by that. And likewise, the blue one had 2 turns also. It changed direction twice. And that's the most it can have. So a fifth degree could have at most 4 turns. Now you can put on your calculator if you like. I have in yellow graphed y equals x to the fourth, and in green y equals x to the fourth minus 15x squared plus 15x. What I mean by this notation right here is I'm telling you this graph will come from a calculator screen that has an x-min and an x-max given by those first ones. So that's how I set my window on that. And the second one is going to be the y-min and the y-max. And if you set your window like that and put in those functions on your graphing calculator, you should get something that looks like this. So what we see here is that the yellow and green look pretty different because we're looking just at a fairly small window around the origin there. And so that's known as local behavior when we're talking about behavior up close. Now, if we zoom this way out, and so if we move the y mins and y maxes and even the x min and x max, and then we graph it on a calculator, the differences we saw in the local behavior become obscured and you don't really see it, and you're seeing what's known as the global behavior, kind of the big picture. If you go back to the back of the classroom and look at it, and seeing the whole forest. So that's kind of the difference between local and global behavior. Notice all these are both fourth degrees, they're even powers, and so you can see in their end behavior, they come and go in different directions. Look at the next screen. So now we're going to look at power functions with fractional exponents, in particular ones that have denominator not 1. So in our AP Prep days, rational functions we defined as a polynomial divided by a polynomial. And so very simple power functions meet then the criteria to also be considered fractional equations. And so I have a couple examples here in the green and the blue. So y equals 1 over x can be thought of as x to the negative 1, which you can see then is a power function, but you can also see it's a polynomial over a polynomial, so it is also a rational function. This is one that these two, actually, both the 1 over x and 1 over x squared, will come up a great deal. And so what I want you to kind of add these to our list of known functions. So my hope is that when you see 1 over x, you get this mental picture of a function that resides in quadrant 1 and quadrant 3. It has a horizontal asymptote of y equals 0, and it also has a vertical asymptote of y equals 0. And y equals 1 over x squared is similar but has some differences. Because of the x squared, the y values will never be negative, and so it's going to live up here in quadrant 1 and quadrant 2. We will sometimes refer to this as a volcano graph, just kind of a way to see that mental picture. It sort of looks like a volcano there. It too has a horizontal asymptote of y equals 0 and a vertical asymptote of x equals 0. So our definition follows down here for what we mean by horizontal and vertical asymptotes. So here is the formal symbolism and the words, the vocabulary that we're going to need to become familiar with. We talked about a little bit of this last year. It's going to become hopefully just second nature this year. So we read this as if the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L, then the function f of x has a horizontal asymptote of y equals L. Okay, so that is as the x values, as we go further and further out to the right and left, the y values are getting closer and closer to 0. That's what we mean for a horizontal asymptote. And then in the green, we see if the limit as x approaches c from the right of f of x is equal to either positive infinity or negative infinity, or the limit as x approaches c from the left of f of x is equal to positive infinity or negative infinity, then we say f has a vertical asymptote at x equals c. So, for example, on this volcano graph, as the x values move in towards 0 from the right, you can see the y values take off and go up to positive infinity. Likewise, as the x values get closer to 0 from the left, the y values take off and go up to positive infinity, and that's why we have a vertical asymptote at x equals 0. So let's see if we can kind of use this knowledge on this next example. So we're looking just for horizontal and vertical asymptotes for y equals 3x squared minus 12 over x squared minus 1. So for horizontal asymptotes, we consider what happens as x gets really, really big in the positive or negative direction. So as x gets really, really big, then the behavior of both the numerator and denominator are going to be determined by the highest powers of x and their coefficients. this minus 12 and this minus 1 are going to become insignificant as x gets bigger and bigger. 100, 1,000, a million, a billion. So this will act more and more like just 3x squared over x squared, which we know is going to equal 3. So the limit as x approaches infinity of f of x, we say is equal to 3. That means that we have a horizontal asymptote of y equals 3. If we factor the denominator, so if we look at this 3x squared minus 12, and then we factor the denominator x plus 1, x minus 1, then we can see that the places where the denominator is equal to 0, 1 and negative 1, as long as they don't have the same factor in the numerator, remember that would lead to a hole in the graph, but since there is no x plus 1 or x minus 1 to cancel that in the numerator, that means that these are going to be vertical asymptotes. So at x equals negative 1 and x equals positive 1, then this graph will approach positive or negative infinity. Okay, a little refresher. Look at the next screen. And so we know now that we can compare. We know what happens if we have a polynomial over a polynomial. So if we have something like, say, x squared minus 3x plus 2 over 2x squared plus x minus 3, then the end behavior, we know that the dominant function is going to be the one with the higher power of x. That'll be the higher order magnitude function. But we can also compare a polynomial function with, say, an exponential. And this might be a little surprising, maybe not. So we're looking at comparing y equals x to the third. This is a power function or a polynomial function with an exponential function y equals 2 to the x. So if we graph on a window that only takes x from negative 4 to 4 and from 0 to 20, this shows us, and I'm just looking at the quadrant 1 behavior here, we can see that that x to the third takes off and it looks like it's getting bigger faster than 2 to the x. So we might think initially that x to the third is a higher order magnitude function than the exponential 2 to the x. But if we expand our window and now go much bigger, we can now see where the exponential 2 to the x, which started out slower than x to the third, has caught up to the x to the third function. And if we go even further out there, we will see their true nature revealed, that in fact the green exponential has not only caught up to the power function x to the third, but is actually far exceeding it. And so what we will learn, and this will be a big thing that we'll talk about in much more detail down the road in AP Calculus, is that exponential functions are higher order magnitude functions than power functions or any polynomial. Exponentials are higher order functions than, I'm going to say, polynomials. Okay? All right, let's give homework 7 a shot.